This tutorial will show how to do a design optimization using Creo Simulate. So we'll continue using our basic rectangular beam. And if you remember that we said we could create some parameters and use that to drive the dimensions in the model. So let's say we use two parameters here for the height and the width of the beam. And we give height and width 20 millimeters initial values. So that's okay. And we can tie some of the dimensions to those values. So if you open the section and edit definition, so instead of 20 millimeters, I can say enter height. Do you want to add this relation? Yes. And for the width, again, do you want to add this relation? Yes. So if we say OK to that sketch, we can go and change the parameters. So let's make it say 40 millimeters by 30 millimeters, and then OK. It doesn't immediately change the model size, but it needs a regeneration. So if you click that, regenerate, and the model is regenerated with the correct height and width of 40 millimeters and 30 millimeters. So what we want to do now is use those height and width parameters in our design optimization. We can go to Simulate, let's say save this model first, and let's go to Applications and Simulate. And as before, I wanted to create a surface region here, and that's where I want to apply a ton of weight, so 10,000 newtons. So a surface region on that area. First I need to create a sketch as before, select one item, but I haven't got a sketch at the moment, so define on that top plane and create a sketch. And I want to create a simple line again from there to there. Stop it as it's vertical, and I want to apply some dimensions to it. Again, 400 millimeters from the base. That's okay. And I wanted to then define the surface that has to be split by this simple line. So that's the line projection again. Let's say okay to that. So now I got two surfaces where I can apply some surface loads on. So if we do a basic analysis now, but just to show you that you can apply some more controls to this. So if you click on AutoGem, you can create a mesh, and that looks like a very sort of coarse mesh, but because ProEngineer, or well, Creo, is based on the P-type technology, P-adaptive technology, the elements themselves can be quite large, but very high order, like third, fourth, fifth order, or even higher, and depending on the results of the adaptivity. Say no to that. What I can do is, though, maybe add more mesh size controls. So geometrical reference, I can do that either on surfaces, volumes, edges, curves, or points. Let's say create a simple sort of volume control, just choosing the entire, well, we need to create a component. Let's choose the entire beam component, and element size, let's say it's about 20 millimeters. Press OK. And if we look at the mesh now, that's a lot more refined. And you can create even a finer mesh at the base where we expect the higher stress concentrations. So I don't want to save this just now. It will be automatically recreated during simulation anyway. So let's say we want to apply our boundary conditions. We go to home and apply a force at the tip of this beam. So we just select this surface. The value is minus 10,000 newtons. And let's do a preview of that. And that's shown okay. And okay to that. And I also wanted to apply a constraint at the base of this. So let's say that I wanted to apply a fully fixed boundary condition there. Press OK. So that's applied as well. And now I can start my analysis. And that's going to be a new static analysis dependent on the fully fixed left hand and 10,000 newtons applied on the right hand. Once the analysis is defined, we can start the run. Click yes, OK to interactive diagnostics. Takes another few seconds to complete, and we can look at the results. So we want to look at von Mises stress. And what we can see here is that the stresses are fine away from the base, but at the base itself, there's some interesting stress concentrations because we have a very hard boundary condition there. It's fully fixed. And that's not a very good boundary conditions because it'll create stress concentrations, singularities, and it may not reflect the actual parts fixture. So to simulate what's happening there at that location, you may need to do a detailed model. But for doing optimization study, that sort of stress concentration will affect what the optimization outcome will be. And we are really interested in the general beam bending stress there. But these stress concentrations are really taking over the behavior from beam bending to very sharp stress concentrations. We can look at the element shapes, show element edges. You can see that there are a few P high order elements there. It can be further refined there, and as more elements are put in or more higher order elements are created there, you'll have higher stress concentrations. So we can do dynamic query, and we can see that the stresses are ranging from say 520, 540, and then the boundary condition here is affecting the stress in this area. And if you do a basic engineer's beam bending theory, like the force was 10,000 newtons, and that's applied at a location about 450 millimeters from the base. So the moment is 4.5 million Newton millimeters, and the y value is the distance from the neutral axis of the beam to the top fiber, let's say, and I is the second moment of area for this rectangle cross section, which is 40 by 30 millimeters. So by using those values, I can create a stress value, which is my upon I, and that's around 560 megapascals. And that's comparing well with my FEA model at the moment, except where I've got these stress concentrations. So what I want to do is avoid these stress concentrations in my simulation, in the optimization. So there's one way of doing that. Let's close that without saving. It is possible to, say, if you look at the details of analysis 1, exclude some of the elements by ticking this box, but that's fine. We can do that, but not in here. We'll need to go to refine model, and under control we will select isolate for exclusion. So we can define, say, points, edges, curves, surfaces, volumes, or components for exclusion. So that will, say, not take into account those element results in either the adaptive calculations or in the design optimization. So we can do that with a volume, for example. We can say define a volume region here, and then say don't use those element results within that volume. So we do that under this volume region here, and that can be done by a simple extrude operation. And it's looking for a sketch, but I haven't defined a sketch, but I will define one on the surface. So that can be a simple rectangle, and I wanted to make the rectangle exactly from that corner to that corner. So creating some references on the fly, selecting that point and starting my rectangle from there, and then going to somewhere here. But again, I want to create another reference on the fly, pressing the Alt key and the vertex. When I release the Alt key, I can find that my rectangle snaps to that vertex. So that's my rectangle defined. I can OK that sketch, and then define how many millimeters I want to extrude that for the volume region. Let's say 20 millimeters in this case. Press OK. So that has defined a volume region now. And that's similar to the surface region we have defined over there. So we can use that volume region to isolate elements for exclusion. So if you go to Control, Isolate for exclusion, and we can define it based on that volume which is already selected, and press OK. If you notice, there's an excluded symbol, and you can find that those controls are listed under AutoGem controls. The first one was the size control, maximum element size 20 millimeters. The second one is volume region, which is excluded from the analysis, essentially for adaptivity or optimization. So we can now go back to our model and rerun the analysis, and yes to that, and yes to that. Let's close that and then look at the results. So looking at the results at the base, they're slightly modified now. There are still, quite sharp stress concentrations, but when I do my optimization on this beam, that volume region will be effectively excluded. If I look at the plot with element edges, you'll find that that volume region is taken into account when the elements are created. So there's a sort of group of elements that are created separately from the rest of the structure. And we can also go and look at a dynamic query, and we can see that around that area, the value of the stress is getting about 540 megapascals. And on the base itself, it should reach theoretically 560 megapascals. Okay, so let's try to use this model for our optimization study. We can close this without saving. And we need to define a new optimization design study. And we want to minimize the total mass with some design limits. So the design limit, as we have used in the design sensitivity study, can be the maximum von Mises stress. So maximum stress von Mises, that's my predefined measure. I can have my own measures as well. I can measure, say, displacements at certain points or maximum displacements, and I make them as design constraints. So let's go with this maximum von Mises stress and then limit that to 200 megapascals. And I wanted to change certain design variables and try to hit this target by at the same time minimizing the mass. So let's try selecting a parameter from the model. The height at the moment is one of the parameters. So I can select that one and try to do a simulation on a single parameter. But it's possible to do simulations with multiple parameters all at the same time. So let's click this button so that it inserts the selected parameter. And that now is shown here as the current value. Minimum is 30, initial is 40, maximum is 50. But I know that 50 may not be enough, so let's say change that to 100. And with the current value, the stress value is high, so let's start from the current value. And initial value is the same as the current value. So the optimization algorithm will look at values of the height between 40 and 100 millimeters to try to minimize the volume and also keep the maximum von Mises stress below 200. So let's say OK to that, and then let's run that. If you look at the study status, we can see where we are, what parameters are currently being studied. So for example, at the moment it's studying the height at 40 millimeters. So the height is going to be changed. So it's taking a 58.9 value and 66 value, and it says the parameter is now feasible, and then trying some other approximations near that value. So it's completed the analysis and it's found that 64.48 essentially satisfied the von Mises criteria, which is around 200 megapascals, and the goal, which is the volume or the mass essentially, is also minimized at the same time. So let's close that and look at the analysis. So we can look at the von Mises stress. So at the optimum value, what we find is that there are still sharp concentrations at corners, but if you look at the stress that's away from the stress concentration area, let's do a dynamic query, we find that the stress around this area, which should give me roughly the beam bending equations, are 200 megapascals. So we can close that. And then we can close that without saving. One other feature is that if you look at information and look at optimization history, it allows you to sort of simulate how the optimization steps were done. So you can click that to see the next shape, the next shape, and the next shape, and the final shape, and then you can accept it as your current shape. Just bear in mind that the optimized value, 64 point something, may not be a sort of desirable height value. You might actually choose 65 exactly with some sort of tolerance value, just to make it more manufacturable. So that completes our design optimization study.